Okay, Assalamualaikum. Okay, today I'll be teaching about satellite motion in a circular orbit. So basically it is from chapter 7, but I have missed this subtopic. If you could remember, I never taught you about this subtopic. So it's what is it? It's about escape velocity. Okay, so it's from 7.3a. So it's a velocity. Everybody knows what is velocity, and this time we learn about escape velocity. So velocity needed to escape from a certain region. Okay, so the equation or the symbol for escape velocity is supposed to be VE. So its equation is 2gm/r or square root 2gr. Okay, so what is escape velocity? So it's basically is the minimum velocity needed for an object to escape from a surface of a planet. Okay, so velocity needed for an object to escape from the surface of a planet. So we take an example in order to explain this concept. So I have an example here is a rocket. Okay, we have a rocket that is to be launched from the surface of Earth. So this is our Earth basically, and this is the surface of Earth. Okay, so we want to launch the rocket from the surface into a space. So the distance for a space is too far, right? And we symbolize it as infinity. So from surface of Earth, as you can see from the graph here, okay, we want to launch the rocket from here, from surface of Earth, r equal to radius of Earth into r equal to infinity. Okay, so we know every object on the surface of above the surface of Earth is having gravitational potential energy, and the general equation is U equal to gmm over small r. So since just now we know that our r is initial r is radius of Earth and final r is infinity. Okay, so for initial r, gravitational potential energy is negative gmm over r. Okay, and the final position is infinity. So we substitute the equation for gmm over r in small r here is equal to 0. So anything divided by here is infinity for here, for the bottom case. Okay, so when small r is infinity, a whole equation, anything divided by infinity is equal to 0. So u infinity is equal to 0. Okay, so the concept here is actually in order to move from the surface, we need the kinetic energy. So this kinetic energy is actually needed in order to overcome the gravitational potential energy, that is final gravitational potential energy minus initial gravitational potential energy. Okay, this gravitational potential energy is converted into this value of change in gravitational potential energy is supposed to be the same as the value of kinetic energy of the rocket. Okay, so if we make up an equation, kinetic energy is equal to u final minus u initial. So it's half mv squared, 0 minus negative gmm over r. So rearranging this equation, we get an equation for this v. Okay, so v here is escape velocity, so it's equal to square root gmm over r. You do it yourself. Okay, how to rearrange the equation is really simple. Okay, so m here is the mass of the planet, of the Earth. R here is the mass radius of the Earth. Or you can express your equation of escape velocity in terms of g. As we know, gravitational acceleration is equal to gmm over r. Rearranging this equation, and then finally you get your VE. Okay, you substitute gm here into here. Okay, gm is equal to gr squared. So gr squared cancelling r, and then finally you'll get your escape velocity is square root 2gr. Okay, so in conclusion, you have two equations of escape velocity, possible equation that you can use, and for your syllabus you have to know how to derive it. So the steps of derivation is starting from here. Okay, we know the kinetic energy is equal to the value of change in kinetic energy, change in potential energy, final minus initial, final 0, initial negative t, mm/r. And then you proceed with rearranging the equation, and finally you get this equation. Okay, thank you very much.